Hello friends, we start a class on sequence of function. This is our 7th class, okay? This is our 7th class of sequence of function. In previous class, we discussed some examples on MN test, okay? In this class, we discuss a theorem on uniformly convergence and some example, okay? And some example, okay? The theory is a consequence of uniform convergence, okay? The theory is a consequence of uniform convergence. So, theorem. If the subset of R and D not equal to 5, okay? Fn be a sequence of function on D, uniformly convergent to F, okay? This is sequence of function which is uniformly converges to F, okay? Let x0 belongs to D dash, okay? D dash be the derived set of D, okay? Derived set means the set of all limit points, okay? x0 belongs to D. And if limit x tends to x0, fn x equal to an for all n belongs to n, okay? For all n belongs to n. Then number 1, limit n tends to infinity, n exists, that is the sequence n is convergent. This is a real sequence, okay? This is a real sequence. Number 2, limit n tends to infinity, limit x tends to x0, fx, this limit is exist, and this is equal to limit n tends to infinity an, okay? Limit n tends to infinity an. This also can be written as fx means n only converges to f, so limit n tends to infinity fnx, okay? Because the sequence of function is uniformly converges to f, so fx can be right as, and limit n tends to infinity n means this, limit x tends to x0 fnx, okay? So it is to be noted that the limit are interchangeable. Here first x tends to x0, then n tends to infinity. Here first n tends to infinity, then x tends to x0, okay? Both are on fnx, okay? So that is the limits are interchangeable, okay? The limits are interchangeable. Clear? So if the subset of R and D is equal to 5, then this is sequence of function on D which is uniformly converges to F, and x0 belongs to D dash, the derived set of D, and if limit x tends to x0 fn x equal to an, then these two conditions holds, okay? Proof. So first we prove this and then we prove this. Since fn is uniformly convergent, okay? This is uniformly converges to the function f. So by Cauchy criteria, for each epsilon greater than 0, there exists rational number k belongs to n such that mod of fmx minus fnx is less than epsilon for all n greater than equal for all m comma n greater than equal to k. This is the alternative condition of Cauchy criteria. Okay, we discussed this in previous classes. Okay, so a sequence is uniformly convergent if and only if the sequence of function satisfy the Cauchy criteria, and this is the Cauchy criteria. Okay, for each epsilon greater than 0 there exists k belongs to n such that mod of fmx minus fnx is epsilon for all m comma n greater than equal to k. Okay, so here we take epsilon, epsilon by 2, epsilon by 3 as my choice. Okay, so we take epsilon by 2. We take epsilon by 2. Okay, clear? Now since limit fnx equal to n, limit x tends to fnx equal to n, so limit x tends to x0, fnx equal to n, and limit x tends to x0, fmx equal to am. Okay, because this is limit x tends to x0, fnx equal to an for all n belongs to n. Okay, so limit fnx equal to n and limit fmx equal to am. Okay, therefore limit x tends to x0, fnx mx minus fnx. Okay, if is am minus an. Okay, because if limit x tends to c, fx equal to l, limit l1, limit x tends to c, gx equal to l2, then limit x tends to c, fx plus minus gx, this is equal to l1 plus minus l2. Okay, so this limit is an, this limit is am, so the difference is am minus an. And we also limit x tends to c, mod fx equal to mod l1. Okay, yes. So this implies limit x tends to x0, mod of fnx minus fmx minus fnx equal to mod of am minus am. Okay, clear? We use these two results on limit of a function. Okay, so if we take limit as x tends to x0 in the both of this inequality. Okay, in the both of this inequality. Okay, so therefore from this is, we take this is number 1. Okay, so from 1 we take there as 1. So from 1 we taking limit as x tends to x0 in the both of 1, we get limit of this, limit x tends to x0, mod of fmx minus fnx is less than equal to epsilon by 2. We discuss in previous class, if we take a limit at the both side of an inequality, then less than becomes less than equal to. Okay, the equality may be occur. Okay, and in the right side the limit does not work. Okay, because there are no x here. So this is am minus an is less than equal to epsilon by 2, which is less than epsilon for all m comma n greater than equal to k. Okay, for all m comma n greater than equal to k. Clear? Since this sequence, this is a real sequence. Okay, it's a real sequence, and this implies the sequence is a Cauchy sequence. Okay, 2 implies this sequence is a Cauchy sequence, and every Cauchy sequence is convergent. Okay, every Cauchy real sequence is convergent. Clear? This implies this is convergent, that is limit n tends to infinity n exist. Okay, so the first part, limit n tends to infinity n exist. Okay, so the first part is done. Limit n tends to infinity n is exist, that is the sequence is convergent. Okay, now the second part. Okay, here we prove limit x tends to x0 f n x equal to limit n tends to infinity n. Okay, so we take this as L. Okay, we take this as L, say. Okay, so let limit n tends to infinity n equal to L. Now in theorem we see that the sequence of function is uniformly converges to f. Okay, so by definition, for each epsilon greater than 0 there exists a natural number k, we take k1. Okay, there exists a natural number k1 such that mod of fnx minus fx is less than epsilon. We can choose any epsilon, so we take epsilon by 3 for all n greater than equal to k1. Okay, now since limit n equal to L, okay, limit n equal to L, so this implies since limit n tends to infinity equal to L, this implies for each epsilon greater than 0 there exists k2 belongs to n such that mod of n minus L less than epsilon by 3 also we choose epsilon as epsilon by 3 for all n greater than equal to k2. Okay, this is a real sequence, and a real sequence converges to L. Then by definition, for each epsilon greater than 0 there exists k2 belongs to L such that mod of n minus L is less than epsilon by 3 for all n greater than equal to k2. Okay, so this is true for all n greater than equal to k1, this is true for all n greater than equal to k2. So both is true for all n greater than equal to k, where k is the maximum of k1 and k2. Okay, so therefore for each epsilon greater than 0 there is epsilon greater than 0 mod of fnx minus fx is less than epsilon by 3, and mod of n minus L is also less than epsilon by 3 for all n greater than equal to k. Okay, here k is equal to maximum of k1 and k2. Okay, this concept is known in real sequence. Okay, clear? Okay, now so for every n greater than equal to k, this true inequality holds. So this implies for each epsilon greater than 0 mod of fkx minus fx, this is less than epsilon by 3, and mod of akx minus L, this is also less than epsilon by 3. Okay, because for n equal to k this is holds, for n equal to k these conditions are holds. Okay, okay, now we have limit x tends to x0 fnx equal to n for all n belongs to n. Okay, for all n belongs to n, and each fnx are from d to what, because the sequence of function defined on the set D. Okay, so this x comes from D. Okay, therefore for these functions domain is D. Okay, so this limit is equal to n for all n. So for n equal to k this is holds, for n equal to k this is holds. Okay, so limit of a function, by the definition of a limit of a function we have for each epsilon greater than 0, there exists delta greater than 0 such that mod of fk minus ak is less than epsilon by 3, satisfying for all x belongs to n dash x0 delta intersection d. Okay, by the definition of the limit, this is our deleted neighborhood. This is our deleted neighborhood of x0 intersection d. Okay, clear? Okay, now we combined this and this. Okay, now we combine this and this. These are 3, this is 4. Okay, so we have to prove that limit x tends to x0 fx equal to L. Okay, we take this as L. Limit x tends to x0 fx equal to L. Okay, so mod of fx minus L is less than epsilon. Okay, now we find mod of fx minus L. Now we find mod of fx minus L. Now we find mod of fx minus L. This is equal to mod of fx minus fkx plus fkx minus ak plus ak minus L. Okay, subtract and add. Minus fkx plus fkx cancel out, minus ak plus ak cancel out, and remainder is fx minus 1. Okay, so this is equal to this. By triangle inequality, this is fx minus fkx. Okay, plus fkx minus ak plus ak minus L. Okay, clear? So by 3 and 4, since fx minus fkx, okay, this is fkx minus fx plus fkx minus ak plus ak minus L. Okay, now fkx minus fx is less than epsilon by 3. This is also less than epsilon by 3, and this is also less than epsilon by 3, satisfying for all x belongs to this. So is less than epsilon by 3 plus epsilon by 3 plus epsilon by 3 for all x satisfying x belongs to n dash x0 delta intersection d. Okay, for all x intersection d. So this is equal to epsilon. So therefore mod of f of x minus L. Therefore, mod of f of x minus L is less than epsilon for all x satisfying. This is true for every epsilon. This is true for every epsilon. Okay. So this implies limit x tends to x0 about the point x0. So x tends to x0. Fx equal to L. Okay, that is limit n tends to infinity L, because we take limit n tends to infinity n equal to L. Okay, limit n tends to infinity n equal to L. Okay, so the second part, limit x tends to x0 fx equal to limit n tends to infinity n is proved. Okay. So hence complete this theorem. Okay. Now we discuss the converse of the theorem. Okay. We consider the sequence of function fnx equal to x by x plus n. Okay. N belongs to natural number and x belongs to 0 infinity. Okay. So this is our domain. Okay. And this is our sequence of function. So we repeat what is our theorem. Our theorem is if fn be sequence of function, and this sequence of function is uniformly converges to f. Okay, x0 be any point in d dash, that is the d dash set of d, that is if x0 is a limit point of d, and at that point this is equal to an, at that point this is equal to an, that is at x0, as x tends to x0, f in x equal to an for all n, then this n is also convergent and the limits are interchangeable. Okay, so we choose x0 belongs to d dash. Okay, and first we check the sequence of function is uniformly convergent or not. Then we take a x0 and check these two conditions are true or not. Okay, first we check this, then we check these two conditions. Okay, so in the discussion of previous classes, we easily find the sequence of function is uniformly convergent, is pointwise convergent on 0 infinity, and the limit function is fx equal to 0. Okay, we discussed so many examples to find the limit function in previous classes. Okay, so this sequence of function is pointwise convergent on 0 infinity, and the limit function fx equal to 0 for all x belongs to 0 infinity. Okay, so now by MN test we check if this is uniformly convergent or not. So what is our MN test? Our MN test is if this sequence of function is pointwise converges to f and Mn equal to supremum of mod of fnx minus fx, then this sequence of function is uniformly convergent if and only if the sequence Mn tends to 0 as n tends to infinity. Okay, so we find this supremum. Okay, so first we find the difference mod of fnx minus fx. Okay, so mod of fnx minus fx is x by x plus n minus 0, because our limit function is 0. Okay, so this is equal to x by x plus n mod of, since this is a non-negative term because x is non-negative or n is positive, so this is non-negative, so we remove the mod x by x plus n. Okay, this can be written as 1 by n by x plus n. Okay, n by x plus n. Okay, now we see n belongs to n and x belongs to 0 infinity. Okay, so n by x plus n, this is greater than 0 for all x and for all n. Okay, so minus n by x plus n is less than 0 for all x for all n. 1 minus n by x plus n is less than 1 for all x and for all n. Okay, so this is less than 1 for all x belongs to 0 infinity and for all n belongs to n. Okay, clear? Okay, and then the supremum Mn equal to supremum of x belongs to 0 infinity fnx minus fx. Okay, this is our Mn, so this is 1 because for every n this is less than 1. Okay, so the supremum is 1. Clear? Supremum is 1. Okay, so we note that the Mn does not converge to 0 as n tends to infinity. Okay, the sequence Mn does not converge to 0 as n tends to infinity, but for uniform convergence the Mn must be tends to 0. This is if and only if condition. This is our Mn test. So by Mn test we can say that this implies the sequence of function is not uniformly convergent. Okay, sequence of function is not uniformly convergent. Now we take x0 belongs to d dash. So what is our d? So our d is 0 infinity. So and we take 0 belongs to d dash because 0 is a limit point of d. Okay, so 0 belongs to d dash. Now what is our an? Our an is limit x tends to 0 fnx. Okay, this is our an. Clear? So this is equal to limit x tends to 0 x by x plus n. Okay, since n is a natural number, so the limit must be 0. Okay, this is 0. So the an is 0. So the sequence is the sequence is 0, 0, 0, 0, and so on. Okay, this is our sequence. This is our n. Okay, so limit n tends to infinity an equal to 0. Limit n tends to infinity an equal to 0, that is limit n tends to infinity, this is x tends to 0 fnx equal to 0. Okay, because an is our this. Now limit n tends to infinity fnx. Now limit n tends to infinity fnx. Okay, so this is 0 for all x belongs to 0 infinity because for every x this is pointwise convergent. For every x the sequence of function is pointwise convergent and converges to 0. So limit n tends to infinity fnx is 0 for every x, and therefore limit x tends to 0, limit n tends to infinity fnx, this is also 0. Okay, so this is also equal to 0, this is also equal to 0, so these two limits are equal. Limit n tends to infinity, limit x tends to 0 fnx equal to limit x tends to 0, limit n tends to infinity fnx. Okay, so we see the sequence an is also convergent, and the limit must be interchanged. The limit can be interchanged, but the sequence of function is not uniformly convergent. Sequence of function is not uniformly convergent. So the theorem says that if the sequence of function is uniformly convergent to f, and we take a point x0 belongs to d dash, and an is this, then an is convergent and the limit is interchangeable. In the example this we see that the limit of n exists, that is n is convergent and the limit are also interchange, but the sequence of function is not uniformly convergent. So this is the example to prove the converse of the above theorem is not true. Okay, now another consequence of uniformly convergence is if D subset of R and this is a sequence of function, be a sequence of function which is uniformly convergent to the function f. Okay, let C belongs to D and for all n belongs to n, Fn is continuous at C. Okay, each term of the sequence of function is continuous at C. Then the limit function f is continuous at C. Okay, so the theorem says that if Fn is a sequence of function which is uniformly converges to f and every term of the sequence of function is continuous at a point C in D, then the limit function is continuous at C. Okay, we does not prove this theorem. Okay, we does not prove this theorem. This you will get in MAPA. Okay, from MAPA and similar as the previous theorem. Okay, the proof of this is similar as the theorem for limit. Okay, so we do not prove this theorem. We give some examples how to use this theorem to check a function is uniformly convergent, a sequence of function is uniformly convergent or not. Okay, so we give some application of this theorem. Now I give example. Let us consider the sequence of function f n x equal to nx by 1 plus nx. Okay, x belongs to 0 infinity and n belongs to natural number. Okay, clear? So since nx is greater than or equal to 0 for all x belongs to 0 infinity and for all n, okay, for all n belongs to n. Okay, this implies 1 plus nx greater than or equal to 1. This implies 1 plus nx is not equal to 0 for all x and for all n. Okay, so we know that if f and g are two functions from R to R, okay, and f, g are both continuous at x belongs to R, then f by g is also continuous at x belongs to R provided gx not equal to 0. Okay, clear? F and g be two functions which are continuous at a point x belongs to R, then the question function f by g. Okay, the function f by g is also continuous at x provided g of x not equal to 0. So this is a continuous function, nx polynomial. This is a continuous function. This is also a continuous function. Okay, so f and x is a continuous function provided 1 plus nx not equal to 0. Clear? So this is not equal to 0 for every x. So f and x is continuous at every x belongs to 0 infinity. Okay, at every x belongs to 0 infinity. Clear? Is continuous at every x belongs to 0 infinity. Clear? By this result, but this is not uniformly convergent. See, now we prove this is not uniformly convergent. How we prove? Okay, so we find this is continuous at every x. Okay, now we find the limit function. Okay, now we find the limit function. Since for x equal to 0, limit n tends to infinity fn 0 equal to limit n tends to infinity 0. Okay, fn 0 means x equal to 0. So for x equal to 0, this is 0. So limit n tends to infinity fn 0 is 0. So this is 0. Okay, so the limit exists at x equal to 0. Therefore, the real sequence is convergent. This implies the sequence of function is pointwise convergent at x equal to 0, and the limit function is 0. Okay, now for x not equal to 0, what is our limit function? For x not equal to 0, limit n tends to infinity fn x equal to limit n tends to infinity nx by 1 plus nx. Clear? This implies limit n tends to infinity, if we divide by n, x by 1 by n plus x. Okay, 1 by n plus x. So for n tends to infinity, 1 by n equal to 0. So this limit will be 1. So the limit exists. Therefore, the real sequence is convergent for all x belongs to 0 infinity. Okay, the real sequence is convergent for all x belongs to 0 infinity, and therefore the sequence of function is pointwise convergent. This is for x not equal to 0. So the sequence of function is pointwise convergent for every x not equal to 0. Okay, and the limit function is 1. So the sequence of function is pointwise convergent at x equal to 0, and the limit is 0. And the sequence of function is also pointwise convergent for every x not equal to 0, and the limit is 1. So therefore, the sequence of function is pointwise convergent on 0 infinity, and the limit function is fx equal to 0 when x equal to 0 and 1 when x not equal to 0. Okay, clear? So this is not continuous. This is not continuous. So this theorem says that if each fn is continuous at C, and fn is uniformly converges to f, then the limit function must be continuous at C. Okay, Clear? Here each fn is continuous at every x. Okay, so at every x each fn is continuous. At every x each fn is continuous. So each fn is continuous at 0. So each fn is continuous at x equal to 0, but fx is not continuous at x equal to 0. Okay, so this implies the sequence of function is not uniformly convergent to f, because if uniformly convergent, then the limit function must be continuous at 0. Okay, because of this theorem. So the sequence of function this is not uniformly convergent. Okay, thank you, that's it.